Hello everyone. In this module, we are going to solve some of the problems based on C13 NMR spectroscopy. Before we go for the problems, we shall quickly brush up our memory regarding the chemical shift values of the C13 NMR because these chemical shift values are very important for solving the NMR problems. We know that whatever comes below 100, it will be saturated carbons. Usually it will be sp3 carbon. Whatever comes beyond 100, chemical shift or delta, they will be unsaturated carbons and they are sp2 carbons. Here we have given in the table the approximate chemical shift values for every kind of carbon that we encounter in the different classes of organic compounds. This is TMS, whose value will be 0. Here this is the delta value. Primary carbon 8 to 30, secondary carbon 15 to 55, tertiary carbon 20 to 60, quaternary carbon 30 to 50. Then coming to carbon attached to different halides, if it is iodine, minus 20 to 40, if it is bromo, 25 to 65, if it is chloro, 35 to 80. So we can see that as the electronegativity decreases, the value is slightly increasing. And if the carbon is attached to oxygen, then it is 40 to 80. If the carbon is attached to nitrogen, then it is 30 to 65. If there is any vinylic carbon, that is unsaturated group, then you will see that there is a drastic change or shift in the transition in the chemical shift value. So far, this is about saturated carbon. When we move from saturated to unsaturated system, you will be seeing that there will be a sudden drift. So for this alkenic carbon, you will see that it will be between 100 to 150. Why the range is so big? Because depending on the groups attached to the different carbons, you will have different chemical shift values. If it is aromatic carbon, then it is 110 to 170. If it is imine carbon, 150 to 170. If it is nitrile carbon, it is 110 to 140. If it is carbonyl carbon of the amide function, then it is 155 to 185. If the carbonyl carbon is from carboxylic acid or ester, then it is 165 to 185. If the carbonyl carbon is from aldehydic or ketonic group, then that will have the more deshielded value of 190 to 220. These values are all approximate values. You don't have to remember the exact value, just you have to remember the range. Based on the range, you will see that different problems can be easily solved based on the C13 NMR data given. Coming to exercise 1. This is problem 1. This is composite problem involving UV, IR, PMR and CMR. The first problem goes like this. Elucidate the structure of an organic compound with the molecular formula C8H8O2 using following spectral data. UV, they have given 250 nanometer. So 250 nanometer indicates that the compound could be an aromatic system. IR 3050, 2850, 2740, 1670, 1230, 820 centimeter inverse. When the more IR values are given, you don't have to worry too much for all the values for assigning the different functional groups. Only the characteristic group frequencies you have to identify. 3050, definitely it will be CH stretching frequency. 1670 may be aldehydic, we are not so sure. Whereas below 900 or 1200, you can really omit because it is from the fingerprint region. You don't have to worry much in many cases. So coming to 1H NMR values, 9.8, 1H singlet. So anything between 9 to 10, it shows that the compound contains aldehydic proton. So this is aromatic region 7.8 and 6.9. Both have got 2H, doublet J is equal to 8 Hertz. So different values with the same coupling constant that refers to disubstituted benzene. And you should observe here that one aromatic region is got more, another aromatic region has got less. It means that the disubstituted benzene is unsymmetrically substituted. That means both the para positions have got different substituents. As a result of that, you have got one more and one less. Maybe this is near the electron withdrawing group and this is near the electron releasing group. And 3.9 3H singlet, maybe it is CH3 but attached to some oxygen or nitrogen. Because the molecular formula has got oxygen, I guess that this should be methoxy group because methoxy is OCH3 ether function. Usually it will have from the range 3.5 to 4. So the new addition here is the carbon 55, 114, 129, 139, 169 and 190. Among these, the highest value is 190. So we are suspecting a aldehydic proton here, and a carbonyl aldehydic here. So hence this may be, this carbon may be carbonyl carbon. Here we have got 55, the least. So it may be CH3 of the methoxy group. We are not so sure. We will see how we arrive at. So before we go for solving the problem, we have to first calculate the double bond equivalent. For that, the formula is CaHbNcOD. You have to substitute in this A plus 1 plus C minus B by 2. Here 8 plus 1 9, and here it should be 0. 0 minus 8 by 2, it should be 4. 9 minus 4 is 5. So it indicates that there are 5 unsaturations in the compound, and 5 unsaturations are coming from one ring and 4 unsaturations. One ring will have 3 double bonds. So 3 plus 1 4. One more should be carbonyl. So I think we can suspect that there is one benzene ring and there is one unsaturated group coming from the carbonyl carbon. UV at 250 nanometer indicates the presence of aromatic system. IR, as I said, 3050 is for aromatic CH, and we are telling that there are 5 unsaturations. So again, this is corroborating with the double bond equivalent. So 3050 should be from aromatic CH group. 1670, it indicates the presence of aldehyde group. Remaining IR values, you can just omit at this juncture. PMR 9.8, 1H singlet, so it should be from aldehydic proton. As I said, these are disubstituted benzene. One is near to electron withdrawing group, another one is near to electron releasing group. 3.93H singlet, it may be due to the presence of methoxy group. So coming to CMR, as I said, this carbonyl carbon will have the highest deshielded value, 190. The least will be for the methoxy CH3 of the methyl. The rest will be for the aromatic carbons. So based on this, the structure can be predicted like this. So this is the structure of the carbon paramethoxy benzaldehyde. Here you are supposed to explain both proton NMR as well as C13 NMR. That is the difference from the previous composite problems to today's composite problem. In the previous composite problems, we were discussing only about the proton NMR in the structure, whereas because C13 NMR is also given in today's session, so you have to discuss about C13 NMR values also in the compound. So for that reason, we have to write the structure first and then assign all the protons for this first. This is aldehydic proton 9.8 singlet, and this is the HA carbon, and this is HB carbon. HA's carbon is near to carbonyl. We know that carbonyl will have both electronegativity as well as the anisotropic effect. So you can give more value for this HA of 7.8 and doublet, because HA is coupling with HP. Then the neighbor is 1, 1 plus 1 is 2. That's why it is appearing as a doublet. And this HB, it is near the electron releasing methoxy group. That's why you can have the less value, 6.9. This is also having one neighbor. That's why n plus 1 rule holds good. 1 plus 1 is 2. That's why it is also doublet. And the last one is the 3.9 singlet for the methoxy. Once we are done with 1H NMR values, now we have to go for C13 NMR values, assign whichever is possible at the first site. So this is carbonyl carbon should have the highest among this is 190. So it should be given for this carbonyl, and the least will be for the methoxy group methyl, that is 55, and the rest will be for the aromatic carbons, because there are no any other carbons present in this compound. Now when you are assigning this, you must be very careful. The next to the highest is 169. That should be definitely this carbon. This is C1 phenyl quaternary carbon. It will not show any multiplicity, and moreover this is the proton decoupled spectrum, in the sense that all the proton couplings are omitted from the CMR scanning, and hence you are getting only singlets here. So 169 for this. Why we are giving 169 for this carbon? Because this carbon is directly attached to the carbonyl carbon. We know that carbonyl carbon exerts both electronegativity as well as the anisotropic effect. And the next highest is 139. That should be definitely this carbon attached to HA. The next list is 129. This is for the HB attached carbon 129. And the last is 114. That should be for this another quaternary carbon attached to electron releasing methoxy group. And this will be the list. So this is how you have to solve composite problem when we also include carbon 13 NMR data. The next problem, write the expected number of signals in the CMR proton decoupled spectrum of the following compounds. So proton decoupled, as I said, here all the proton couplings are noise decoupled, and hence you are going to get only the singlets, only such singlets. He's asking how many such singlets can be seen. Rather, we have to say how many different types of carbons are present in these kind of compounds. So in this compound, we have to first observe that how many types of carbons are there. There are CH2s and CH. How many CH2s are there? 1, 2, 3, 4. This is 5. You have to observe here that these 4 CH2s, methylene groups, 1, 2, 3, and 4, they are all in one different environment. And this CH2 is in different chemical environment, whereas these two CH are in different chemical environment. So essentially, this compound should show 3 different signals in the CMR spectrum. That is what we have seen here. So this methylene 1, 2, 3, 4, all marked in red are 1 carbon, all marked in red, blue are in 1 carbon, one marked in purple or pink, it is one type of carbon. So this compound essentially has got 3 different kinds of carbons, and as a result of that, we are going to get 3 singlets in the CMR spectrum. They are not asking to assign chemical shift values, they are just asking you to write the expected number of signals, so you don't have to worry at this point of time about assigning the chemical shift values. Next, this compound. So this compound has got both CH2 and CH, and you have to observe here that all the CH2s, there are 6 CH2s, 1, 2, 3, 4, 5, 6. All the CH2s, 6 CH2s are present in one type of environment, whereas this CH, it is present in one type. Both the CH are present in one type of chemical environment, and essentially you should get 2 types of signals in the CMR spectrum. Whereas the own compound, the ketonic form of this more substituted and bulkier group, here you can see that all the carbons are present in different environment. Here there are CH2, Carbonyl, and CH as well as CH3. You will see that all are present in different chemical environment. So we'll start from here. This is 1 CH, this is 2 carbonyl carbon, this is 3 CH2, this is 4 CH, this is 5 CH2, 6 CH2, this is 7 quaternary carbon, this is 8 CH3, 9 CH3, and 10 CH3. You can ask that both these methyl groups are present in same chemical environment, but the answer is no, because here this CH3 will have the influence of carbonyl, whereas this CH3 will have the influence of this methyl, and hence both the methyl groups are present in different chemical environments, whereas this methyl is also present in different chemical environment. Here it has got CH2, on this side it has got the carbonyl, and then essentially you should have 10 signals or 10 peaks in the CMR spectrum. So the third question, how will you distinguish between ortho, meta, and para dihydroxybenzene on the basis of their C13 NMR spectrum? This we have discussed in the previous module also, and they have given the same question. Here this is dihydroxybenzene. You know that dihydroxybenzene, it exists as 3 isomers, ortho isomer, meta isomer, and para isomer. The ortho isomer, we have to write, this is essentially a substituted phenol. Ortho isomer should have hydroxide, the ortho group. This phenol having meta hydroxy is called meta isomer, and this phenol having para hydroxy is the para isomer. Now we have to count how many different types of carbons are there. Here, both these carbons are present in same environment. These 2 carbons are in different environment. These 2 carbons are present in different environment. So you should get 3 different types of signals for the ortho isomer. For the meta isomer, this is different, these two are different, these two are different, this is different. So 1, 2, 3, and 4. So if you get 4 signals in the CMR spectrum, you can say that the isomer is meta. Now coming to para, if you remember in the last module, we have said that if you get the least number of signals in the CMR spectrum, then that substituent will be the para isomer. Why? This is para hydroxy dihydroxy benzene. So this carbon and this carbon, they are present in same environment, whereas all the 4 carbons of the aromatic region are present in one type of environment, and hence as a result of that you are going to get only 2 signals. So if you are given dihydroxybenzene and ask you to identify which isomer is that, so you just have to simply scan that compound for C13 NMR, and based on the number of signals obtained, you can say whether the given compound is ortho or meta or para, depending on the number of signals you get. Next problem, the central carbon in A, so this is A and this is B, is asking the central carbon in A resonates at 198 ppm, while in B, central carbon absorbs at 254 ppm. Why? So this is the carbocation based on the methane, substituted methane. This is methyl diphenyl methane carbocation, and this is dimethyl phenyl methane carbocation. Here this A carbocation, it is resonating at 198 ppm, whereas the B carbocation is resonating at 254 ppm in the carbon spectrum, and he's asking what is the reason for this. The reason is very simple. If you carefully observe this molecule, you just have to split this and write, you just have to open up this and write, instead of pH you write the benzene ring, instead of pH you write the benzene ring. So if you write the benzene ring, automatically you'll be getting the answer. So this is resonance stabilized. Here there are 2 phenyl ring systems. When there are 2 phenyl ring systems, you will see that there will be more resonance. Because of the resonance, this carbocation will be less de-shielded, or it is more shielded. As a result of that, it is appearing at 198 ppm, whereas in this B carbocation you have got only 1 phenyl, so it is less resonance stabilized. As a result of this carbocation, it will be absorbing at very high de-shielded value of 254 ppm. So the answer here essentially is the resonance stabilization. Here it is more resonance stabilized, this carbocation, whereas this carbocation is less resonance stabilized. Next problem, write the number of peaks that would be obtained in the CMR spectrum of each of these compounds. So it is more or less a kind of second problem, but in different way. The first question is benzene. So this is benzene. We know that in benzene, all the carbons are present in the same environment. So it is giving only 1 peak. Next is cyclobutane. This is cyclobutane. It is a symmetrical molecule, and hence all the carbons are same. So you are going to get only 1 signal. Next is cyclohexane. Here there are 6 carbons, and all the 6 carbons are present in the same chemical environment. As a result of that, you are going to get only 1 signal. The next is 1-chloropentane. So the base is pentane. So you must write 5 carbon atoms, 1, 2, 3, 4, 5. At the first position, you should substitute one of the hydrogens by chloro. So this is 1-chloropentane. If you just look at this molecule, you will think that, okay, there are only 1, 2, and all these methylene groups are present in same environment. But if you scan the C13 NMR spectrum of this, you will see that there are 5 different types of carbons. That meaning all the 5 carbons in this pentane are present in different chemical environment. This is CH3 having CH2. This is CH2 having CH2. This is CH2 having CH2. This is CH2 having CH2. But this CH2 is having chloro, and you should see that this CH2 is near to chloro, whereas this CH2 is near to CH3. And as a result of that, you will see that 5 different signals are obtained. So this is the C13 NMR spectrum of 1-chloropentane, and you will see that you will have 5 different peaks, 1, 2, 3, 4, 5, and all appearing at different chemical shift values. So this shows that in chloropentane or 1-chloropentane, all the 5 carbons are present in different chemical environment. The next problem, hexane 1. So this is essentially an alkyne system. So there should be a triple bond. Hex means 6 carbon atoms. So the base is 6. So you must write hexane first, and at the first position you should put a triple bond. 1, 2, 3, 4, 5, and 6. This is hexane. So how many types of carbon you will have, or how many signals you are going to get in the CMR spectrum of hexane 1? So the answer is simple, and it is 6. Just like the previous problem, 1-chloropentane, here also all the 6 carbon atoms are present in different chemical environment, and as a result of that you are going to get 6 different peaks. 1, 2, 3, 4, 5, 6. So these 2 carbons with the alkynic system. So alkynic, we know that it is unsaturated system, and this is sp hybridized. As a result of that, these 2 will be appearing at more deshielded region, whereas the rest of the 4 carbon atoms, they appear in the saturated region between 0 to 40. The next problem, but1-ene. So but, the base is butane. You must write 4 carbon atoms, 1, 2, 3, 4, and at the first position you should put a double bond. So in this case also you will see that there are 4 different signals. 1, 2, 3, 4, and all the 4 carbon atoms are present in different chemical environment. Here it is alkenic type. We know that alkenic is 100 to 160. So essentially these 2 carbons should be having more deshielded value. It is coming around 115, and another one is coming around 135. And you must observe that always the terminal alkanes will give more, whereas the terminal alkenes will give more, whereas internal alkene will give less values. The next is ethyl benzene. So this is the structure: ethyl substituent CH3CH2 attached to benzene. And here, when we count the number of carbons, you will see that 1, 2, 3, 4, 5, 6. So you should get essentially 6 different types of carbons, and these 2 will be definitely these 2, because these are saturated system, and hence the value will be less. That will be coming in the shielded region, whereas the rest are the aromatic protons. Aromatic protons fall in the range between 110 to 170, and this will be definitely coming in the aromatic region. So here this carbon is different: 1, this 2, 3, and 4, and you will see that these 2 peaks are merged here. You cannot see completely, but when you zoom the spectra, but here you can see one is short and one is slightly long. Based on that, you can say that there are 4 aromatic peaks and 2 saturated peaks. We will now move to the next problem, 6th one. Give a structure or structures consistent with each of the following sets of CMR data. So he has given the molecular formula, and he has given the multiplicity along with the chemical shift values. So based on that, you have to arrive at the probable structure of the compound. And the first one is C3H5Cl3. When such a kind of compound is given, so first you must calculate the DBE, just to be sure that how many number of unsaturations or double bonds are there in the compound. Based on that, it will be easier for you to identify which compound the given data would be suitable to. So for this C3H5Cl3, when you calculate DBE, there will not be any unsaturation. DBE is 0. So this should be essentially a haloalkane type of compound, but it is maybe a branched compound. We are not so sure. So C3H5Cl3 is given the off resonance decoupled spectral data, because once he has given triplet and doublet. In proton decoupled spectra, we get only singlets, whereas in off resonance decoupled spectra, we get different multiplicities. Triplet refers to there is presence of CH2. Doublet refers to presence of CH. So this CH is having 59, whereas CH2 is having 45.3, and there are 3 chloro groups in the compound. So we know that whenever there is any halogen, that too, when it is chloro, you will see that there will be more deshielded value because of the electronegativity coming from the chlorine. So here first, what you have to do, you have to write 3 carbons, 1, 2, and 3. Now you have to keep on satisfying the multiplicity. Triplet, that means you have to first write CH2, and doublet you have to write first CH. And for this CH, you have to attach one Cl. So essentially, this is the structure of the compound. There will be two CH2s and there is one CH, and to all the carbons there will be attached one chloro. And the middle one will be having more value because it is having the neighboring group effect of the chloro. And to this carbon, you will see that both the chloros will have the influence. And whereas this carbon, there will be only two, and for this carbon, there will be only two. And this is essentially a symmetric molecule. So this is the structure of the molecule that you can write based on the given data. The next problem is C3H5Br. So it is a bromo-containing compound. One is triplet coming around 32.6. Another one triplet coming around 118.8. Another one doublet coming around 134.2. So here you can clearly distinguish that there are two types of carbons. One is saturated carbon, and another one is unsaturated carbon, because the value is quite high, above 100, 118, and 134. Essentially, there must be a double bond, and also DBE for this molecule comes out to be 1. It refers to that there is one double bond in the molecule. So triplet, that means there should be one CH2. Another triplet, there should be one more CH2. So there are two CH2s and one CH because it is a doublet. So you must write CH2, CH, CH2, and you have to attach Br. Where you can attach Br is at this juncture because it is given as triplet. So there are two CH2 and one CH and another one Br. The next compound, and also you can, if you want to assign the chemical shift value, you can do so. One CH2, so it should come as a triplet because two hydrogens are directly attached to this. So this triplet will have 118, whereas this doublet will have 134. As I said earlier, the terminal alkenes will show lesser chemical shift value, whereas internal alkenes will always show higher chemical shift value. And another one is CH2. This CH2 is coming as triplet, and this triplet is attached to bromo. That's why you are having for this methylene group more chemical shift value of 32.6. We will now move to the next problem, next set of data, C4H8Br2. So you will see that here there are 4 carbons and there are 4 values. That means to say that all the 4 carbons in the compound are present in different chemical atmosphere. Quartet 10.9, triplet 29, triplet 35.5, doublet 54.3. So quartet means there should be CH3, triplet CH2, triplet CH2, doublet CH. And also you can see that all the carbons are saturated as there is no value above 100, and hence the structure is this. So this is 10.9 because it is a quartet, and this is 29. You have to give 29 for this and 35.5 for this because this carbon is directly attached to bromo, whereas the middle carbon is having 54.3 and it is attached to bromo. So this is the probable structure based on the data given. The next compound, that is C6H10, there is no halogen in this, and in this you can, based on the number of data, you can see that there are 3 different types of carbons, and hence we are getting 3 different signals in the CMR spectrum. One is triplet 22.9, another triplet at 25.3, and there is one doublet 127.2. So there are 2 kinds of carbons in this based on the chemical shift value. These 2 should be saturated carbons, whereas this is unsaturated carbon, and this unsaturated refers to alkene. And when you calculate the DBE for this, it comes out to be 2. So one is for this alkene double bond, and there is one more DBE. So, and there are only 3 types of carbons. When you write 6 carbons in the aliphatic region, you will not satisfy this data, and hence when you put it in the form of a ring, so DBE is also satisfied. This molecule is essentially cyclohexene. So again, when you cut the molecule like this in the horizontal fashion, you will see that the molecule is symmetric. So above 3 carbons are exactly equal to that of the below carbons, and hence you have got only 3 types of carbons in the CMR spectrum. and this is doublet 127.2. These two are doublets. This carbon is having one hydrogen, this carbon is also having one hydrogen, that's why you are having a doublet here. And these two carbons should be 25.3 because they are close to this alkene group, whereas these two carbons are also triplet and having less chemical shift value of 22.9. So the distinction between these two, this is 22.9 and this is 25.3, because this carbon is near to double bond, there will be some influence, whereas this carbon is far away from this double bond, and as a result of that, this carbon will have lower chemical shift value, whereas this carbon will have higher chemical shift value. Now we will move to the next problem, seventh one. Give a structure or structure consistent with the following CMR spectrum. So in the previous slide, you will see that you saw that the data is given, the multiplicity and the chemical shift values are given, whereas in this problem, they have given the CMR spectrum directly and asked you to find out the structure or structures of the compound. Now, essentially, when you see this CMR spectrum, you will see that at the first side, there are two types of carbons. One is saturated and another one is unsaturated. So here, and look at the intensity of this peak. So whatever is coming here, this should be necessarily CH3. And when looking at the intensity of this peak, I can say that there will be more number of CH3s in this compound, and this may be either CH or CH2, we are not so sure. And also they have not given the molecular formula, so you should be very, very careful while predicting the structure of this compound. And here there is a peak at roughly around 108 ppm and another peak around 155 ppm. So these tell that there should be a alkene bond, because one is internal, another one is terminal. So usually the internal will show high deshielded value, whereas terminal will show less deshielded value. There should be CH double bond CH, and there should be CH3, and this CH3 should be in very high intensity. So there could be a tertiary butyl group, and this may be a CH or just a C. So based on that, you can say that this is the formula that fits into this spectrum. This is 3,3-dimethyl 1-butene. Here, based on the intensity, I have predicted that there are 3 methyl groups. So this is a tertiary butyl group, and all the 3 methyl groups are present in the same chemical environment, and all are appearing around 29.5 or 30, you can roughly say. And this quaternary carbon is appearing around 33.7. This is the one, whereas the alkene one is coming around 106.7 and another one is around 155. So there are 1, 2, 3, 4 different kinds of carbons, and hence you are getting 1, 2, 3, 4, 4 different kinds of peaks in the CMR spectrum. So this is 3,3-dimethyl 1-butene. So you should be prepared for answering both kind of questions. One when the spectrum is given, the another one when the data is given. Next compound. How do you distinguish between styrene and ethyl benzene on the basis of their C13 NMR spectrum? So they have given just the names of the compounds as styrene and ethyl benzene. So when such a question is asked, first you should essentially write the structures of the given compounds. So styrene, it is alkene attached to benzene. Ethyl benzene is ethyl group attached to benzene. So this is styrene and this is ethyl benzene. At the first sight, you can clearly see that there is alkene group and there is no alkene group. Both have got aromatic ring, no doubt. But what about the side chains attached to this benzene ring? Here the side chain is a double bond. Here the side chain is an ethyl group. So styrene will show 2 protons at the alkenic region. Say around one is terminal, another one is internal alkene. This will be around 110 and this will be around 150. So you will have 115 and 110 groups along with the aromatic carbons. Whereas in ethyl benzene, there will be 2 types of protons. One is saturated and another one is unsaturated. Whereas in styrene, you will see that all are unsaturated carbons. Whereas here you will see that there are both saturated carbons as well as unsaturated carbon. This should be essentially CH3 and CH2 coming in the range between say 20 to 40 roughly, and the rest is the aromatic protons. So styrene has a double bond and hence peak appear at alkene region, whereas in the case of ethyl benzene, there will not be any peak at alkenic region, but two peaks appear at secondary and primary methyl group, that is CH3 and CH2. The next problem, in 2-butanone, the carbonyl carbon absorbs at 207 ppm, whereas in but1-ene-3-one, the carbonyl carbon resonates at 194 ppm. Why? When such a question is asked, first you should write the structures of the compounds. One is 2-butanone, so but, that is the base, 4 carbon atoms. At the second position, you should put a carbonyl group. So 1, 2, 3, 4, 4 carbon atoms. So this is butane. At the second position, if you put one, this becomes 2-butanone. Whereas in the case of but1-ene-3-one, here also the base is but, so you should write 4 carbon atoms. At first position, you should put a double bond because 1-ene is a double bond. At first position, you put a double bond, and at third position, you put a ketone, ONE. This is a ketone. So this is 2-butanone. This is but1-ene-3-one. Now, the question that is asking is, in 2-butanone, this carbonyl carbon is absorbing at higher value, 207 ppm, whereas in this but1-ene-3-one, the carbonyl carbon is resonating at lesser delta value, about 194 ppm. What could be the reason? So if you simply look at the structure of this compound, you will see that here the lone pair of electrons on this oxygen will be coming here, this double bond will move here, and this carbon will be getting a negative charge. So there is resonance effect in this compound because of the presence of unsaturated system present in the ketone. And this is alpha beta unsaturated ketone. So because of the resonance, it will be showing less delta value, whereas here there is no resonance, and as such the carbonyl carbon is appearing at higher delta value, that is more deshielded region of around 207 ppm. So the positive charge on the carbonyl carbon gets reduced due to resonance in the unsaturated ketone. So when it is moved here, this carbon gets a positive charge, and the positive charge on this here gets reduced because of the resonance in the unsaturated ketone, and this is the reason why this alpha beta unsaturated ketone is resonating at lesser delta value, whereas this just a ketone is resonating at higher delta value. So this is all about different kinds of problems based on C13 NMR, and also composite problems involving UV, IR, PMR and CMR that we have studied in this module. So if at all you have got any doubts, please ask questions on the YouTube channel. Thank you very much.